Hello everyone. In the last video, Dr. Subrahmanyam garu delivered a lecture on fundamental units of chemical substances, that is atoms, molecules, ions. In this class, he is going to deliver a lecture on electronic configuration of elements. I hope you all will go through these fundamentals. Thank you.
Thank you, Dr. VRAO, for inviting me to a second lecture. As you put it, in this class, I would like to go to discussion of basics of electronic configuration. For that, I start with a famous equation, Max-Planck equation E is equal to h nu is equal to hc by lambda is equal to hc nu bar. Now, this equation is based on two very important experiments called number 1 photoelectric effect, number 2 black body radiation. Radiant energy can be in the form of discrete units called photons, and h nu represents a photon of energy. Now, radiant energy can be absorbed or emitted in the form of radiation in the form of photons only. Okay. Now, as you can see in the board, I have given you the terms and units also. Now, the frequency of radiation is inversely proportional to wavelength, and inverse wavelength is given by wave number, and these units are employed in spectroscopy. Now, let me go in hydrogen spectrum. We can observe discrete lines both in emission spectrum and also in absorption spectrum. To explain these discrete lines in hydrogen spectrum, Niels Bohr proposed that in hydrogen atom, energy levels are also quantized, given by another famous equation, mvr is equal to n h by 2 pi. In hydrogen, we have 5 series of emission spectra, and to explain these emission spectra, Niels Bohr proposed quantization of energy levels inside in hydrogen atom, as given by the equation mvr is equal to nh by 2 pi. Now, he proposed circular orbits in case of hydrogen atom. Now, based on Niels Bohr theory, to explain multi-electron spectra became very difficult. Say, in case of helium, we have 2 electrons in n is equal to 1 level in circular orbit, suppose, but they have inter-electronic repulsions. These repulsions are not taken into account in Niels Bohr equation. Therefore, to explanation of helium emission spectra or absorption spectra is failed by this Niels Bohr equation. In order to overcome this difficulty, Sommerfeld proposed elliptical orbits, where he proposed 2 quantum numbers. N is one quantum number proposed by Niels Bohr. Sommerfeld proposed 2 quantum numbers by assuming that electrons in an atom revolve not in circular orbits, but in elliptical orbits. And he is able to explain to some extent the spectral lines of helium. But of course, he failed in explaining the spectra of other multi-electron atoms. Now, during 1920s, the physics is in turmoil. Great scientists like Einstein, Planck, Niels Bohr, Rutherford, Paul Dirac, etc., they are struggling to put physics on a right pedestal, because Newtonian physics of exactly locating a particle and knowing its momentum is failed in the case of microparticles like electrons. Right. Now, it is not possible to exactly locate the position and momentum of electron inside an atom is proposed by Heisenberg's uncertainty principle. Because in Newtonian physics, we can exactly locate the position and momentum of a moving body, that is our GPS system. But in case of microparticles, it was not the case, because when you want to observe the position of an electron, a small particle like electron, a photon is to be impacted on that. Photon and electron are having similar sizes. So, photon impact displaces electron position. So, it is not possible to exactly locate the position of electron. Consequently, its momentum also cannot be exactly determined. So, Heisenberg proposed that the uncertainty in position multiplied by uncertainty in momentum is given by a constant h by 4 pi. So, you cannot make delta x 0 or even delta p 0. You can approximately say that electron is located from a distance of r plus delta r or x plus delta x, having a momentum between p plus delta p. Only approximate values can be calculated according to Heisenberg's uncertainty principle. The basic properties of light, reflection, refraction, diffraction are very well explained by wave nature given by famous Maxwell equations. So, Davison and Jerner conducted an experiment where electrons show diffraction pattern similar to that of radiant energy or light. So, they proposed wave nature for electrons. Now, a famous scientist Schrodinger combined the particle nature of electron and wave nature of electron into an equation called wave equation. The Schrodinger equation I have given on the board. Now, in this equation, the psi represent a wave function, and that m represent mass of electron, E represents total energy, V represents potential energy. Now, the other form of equation h psi is equal to E psi is a mathematically saying an operator formalism it is called. We do not have to worry about it, but the solution to this equation is important for us. Now, as a part of solution for this second order differential equation, we get a very large number of solutions. Out of these solutions, we select certain solutions which are applicable to our individual case of atoms or molecules or ions. They are called eigenfunctions, right. Now, as part of solution to this wave equation, we got 3 quantum numbers. Now, before solving this equation, the whole equation is converted into polar coordinates. Now, these x, y, z coordinates are changed into polar coordinates, and mathematically this equation can be solved much more easily compared to this Cartesian coordinate equation. Now, in polar coordinates, we have r, theta and phi. R represents radial distance, theta phi represent angle of electron rotation inside an atom. Now, we get 2 parts of a wave function, one depending on radial distance r, the other depend on the angular positions theta and phi. Now, radial wave function and angular wave function we can call them. Now, radial wave function indicates a property of electron. Angular wave function represents the orbital of an electron. Why orbital? It is to satisfy Heisenberg's uncertainty principle. Electron cannot be exactly located at a particular distance from the electron. So, we can say there is a probability function involved. Psi as such has no physical significance, but psi square is related to the probability of finding electron around nucleus, and that is important for us as far as chemistry is concerned. We have as a part of solution for this Schrodinger wave equation, we get first a set of 3 quantum numbers given by the letter symbols capital N, small l and small ml, or numbers like n integer values 1, 2, 3, 4 etc., L 0, 1, 2, 3 etc., and ml minus L plus 1 minus L plus 2 0, then plus up to plus L, we get numbers. We can represent them on the board separately. Now, we are getting a fourth number if we solve this equation based on Einstein's theory of relativity. That fourth quantum number is spin quantum number ms. Okay? Now, to represent the position, momentum and or energy of an electron inside an atom, we require a set of 4 quantum numbers. They are N, L, ml, ms. Now, as a Schrodinger wave equation, solution can be resolved into 2 parts. One is radial wave function, other one is angular wave function. The radial wave function indicates a primary quantum number n. The n indicates the average distance between electron and the nucleus, whereas this angular wave function theta phi, that indicates the contour of the orbital. What is an orbital? Orbital is a region of space around nucleus where electron is likely to be found, or I can say it represents a contour of electron density or charge density, or electron cloud or charge cloud. Now, let me go a bit further. We get a set of 4 quantum numbers. I represent these quantum numbers on board, and then we can explain the significance of each quantum number one by one, right? Yes. I represented the set of quantum numbers on the board N, L, ml. Let us first discuss these 3 quantum numbers. As I explained, n is principal quantum number given by both letter symbols and a number, and also L and also ml. L depends on n, ml depends on L. Now, starting with n is equal to 1, we can represent L ml. L represents subshell, ml represents number of orbitals present in a subshell. Now, n is equal to 1, L becomes 0, ml becomes 0, and that is given the letter symbol S, and the shape of the orbital, that is theta phi wave function, is spherical. So, the sign of wave function is plus in a spherical s orbital. Now, if n is equal to 2, we have 2 sublevels 0 and 1. 0 represents s orbital and 1 represents p orbital. P orbital contour is dumbbell having 2 lobes. One lobe contains plus sign, the other lobe contains minus sign. We represent these shapes in our next video, but presently you imagine the 2 lobes having plus and minus signs separated by Now n is equal to 3 represents 3 subshells 0, 1, 2. It means S, P and D represents 3 represents d orbital. Now n is equal to 4 has 4 subshells 0, 1, 2, 3, 4. 1, 0, 1, 2, 3 only. Now 1 represents 0 represents S, 1 represents P, 2 represents D and 3 represents F orbitals. Now the number of orbitals in each subshell is given by quantum number ml. In fact, it shows us the orientation of an orbital in a magnetic field. Now I have given the numbers. L0 means ml is also single valued 0, that is s orbital is a single in each subshell. So every major level contains single s orbital. Now n is equal to 1 means p orbital. Now we have 3 orientations of p orbitals inside a magnetic field. So starting with n is equal to 2 major level, we have a set of 3 p orbitals. Similarly, starting with n is equal to 3, we have a set of 5 d orbitals. Starting with 4 principal quantum number, we have a set of 7 f orbitals. Now the orbitals in a sublevel are degenerate, that is orbitals of equal energy. Now each orbital can accommodate a maximum of 2 electrons with opposing spins, which is given by spin quantum number ms, which is values are plus or minus half. Okay. Now using this kind of approach, we can write an electronic configuration of elements by a method called NL to the power x method. Now in multi-electron atom, we can represent electronic configuration in simple format NL to the power x. Now this n represents primary quantum number, L represents subshell and x represents number of electrons present in the subshell. Now in multi-electron atom, the various subshells in major energy levels are affected by certain factors like effective nuclear charge, penetration effect, screening effect, etc. So the energy levels are a kind of jumbled. We can discuss the actual arrangement of electrons in a multi-electron atom by taking 3 principles into consideration. One is called build-up or Aufbau principle, second one is called Pauli's exclusion principle, and third one is called Hund's rule. So in the next video, I would like to elaborate on these 3 topics. Thank you, Dr. VRAO, for giving me this opportunity.